Here's an example of retrosynthetic analysis of a conjugated diene. Conjugated dienes come from allylic bromination reaction and subsequent elimination. So let's go ahead and review allylic bromination. Here is an endocyclic alkene, disubstituted alkene. And in this example, we have 4 secondary allylic hydrogen atoms. So since we have the same degree of substitution at both allylic positions, it doesn't matter which hydrogen atom will be replaced with bromine. N-bromosuccinimide serves as in situ source of bromine radicals, diluted bromine atoms, and with the use of N-bromosuccinimide and UV light under free radical reaction conditions, one of these allylic hydrogens will be replaced with bromine. So let's go ahead and replace this hydrogen atom with bromine, and now we have a secondary allylic bromide. Subsequent elimination of HBr using strong base such as sodium or potassium hydroxide. So base will remove the most acidic hydrogen, which will be an alpha hydrogen, alpha relative to the alkyl bromide. So here's our alkyl bromide unit. And we have 2 alpha hydrogens that potentially can be eliminated. Notice that the vinylic hydrogen is not, that's also an alpha hydrogen, but it's not acidic and it will not undergo elimination. So base will attack one of these acidic alpha hydrogens. The sigma bond between the carbon atom, alpha carbon, and the hydrogen to be eliminated will break. 2 electrons from this bond will collapse toward the incipient pi bond, and bromide, the leaving group, will be replaced to form a conjugated diene. So we'll have a new double bond with 2 vinylic hydrogens plus HBr will be eliminated. So again, base deprotonates the alpha carbon, carbon next door to the alkyl halide, bromide is expelled, and we form a double bond. So one more example using an open chain alkene. Here we have a 6-carbon chain with the alkene between carbons 2 and 3. And the reaction conditions indicate that we'll have a free radical allylic bromination. So let's find the most highly substituted allylic hydrogen that will be replaced with the bromine atom. So here we have a primary allylic carbon, and therefore these 3 hydrogens are primary allylic. And here we have secondary allylic carbon with 2 secondary allylic hydrogens. Bromine will selectively replace one of these secondary hydrogens, giving us secondary allylic bromide. Once we installed the bromine atom at the allylic position, we'll go to the carbon next door, the alpha carbon that has hydrogen atoms that can be eliminated. So we have 2 alpha carbons next to the alkyl halide carbon. Here is vinylic carbon, and vinylic hydrogens are not acidic, so we will not consider that hydrogen atom. And here we have secondary carbon with 2 acidic hydrogen atoms. Base will deprotonate alpha carbon. This bond will break, will form the pi bond, and the bromide will be expelled, giving us conjugated diene. So again, to prepare a conjugated diene, you start with an alkene, perform allylic bromination, followed by deprotonation and loss of HBr. So let's go ahead and take a look at our conjugated diene and see if we can propose retrosynthetic analysis. So we have a conjugated diene, the immediate precursor to a conjugated diene, is an allylic bromide. So let's go ahead and keep this double bond. And again, it doesn't matter which alkene you choose to keep since there are two of them. And we'll install allylic bromide at this position. We have two allylic carbons if this is not a double bond here. So if we start with this alkene, then we'll have allylic carbon here, which will be primary, and carbon here, which will be secondary. Therefore, the allylic bromide will be at the secondary position. So our immediate precursor will be secondary allylic bromide at carbon number 3. So 1, 2, 3, 4, 5, and 6. We keep our alkene, carbons 4 and 5. And at carbon number 3, we'll now have hydrogen and bromine. So now we have secondary allylic bromide, which has an immediate precursor in the form of an alkene, simply a double bond. If we have an alkene and we have allylic hydrogens, we can brominate, we can replace those hydrogens with bromine. So our immediate precursor will be an alkene without the bromine atom. We'll have a hydrogen here instead. So precursor will be 2, 3, 4, 5, and 6. With the alkene between carbons 4 and 5 and the two hydrogen atoms at allylic position. So here's our alkene, and precursor to an alkene is an alkyne. So it will be a 6-carbon atom chain with the triple bond between carbons 4 and 5. So 1, 2, 3, 4, triple bond, 5, and 6. Here we have a disubstituted or internal alkyne, which means that we'll prepare it by a twofold alkylation of acetylene. So let's take these two groups apart one at a time. So precursor to disubstituted alkyne is monosubstituted alkyne. So carbons 1, 2, 3, 4, 5, hydrogen atom. So 1, 2, 3, 4, and 5, plus the Rx, which will be simply carbon number 6 with some kind of leaving group. So CH3 bromide, for example. Precursor to monosubstituted alkyne is acetylene, R-acetylene, and alkyl halide. So carbons 1 through 3, 2, 3, will come from an alkyl halide, our Rx, and carbons 4 and 5 will come from acetylene. So going forward now, we have chain extension number 1, followed by chain extension reaction number 2, followed by reduction of the alkyne to transalkene using sodium in liquid ammonia, metal dissolving conditions, and then transalkene will undergo allylic bromination to give us secondary allylic bromide, followed by elimination of HBr to give us conjugated diene. So the synthesis will involve treatment of acetylene with strong base, sodium amide, in liquid ammonia, which will form acetylide ion in situ, and that intermediate will be then treated with alkyl halide, and addition of alkyl halide will allow us to extend the chain, giving us precursor E. We'll extend chain one more time. We'll deprotonate terminal hydrogen, terminal carbon. So another deprotonation with sodium amide in liquid ammonia, followed by addition of carbon number 6, which will be added in the form of methyl bromide, CH3Br. This will be our second chain extension, giving us alkyne D. We'll then reduce alkyne to an alkene in trans fashion, so we'll need metal, sodium or lithium in liquid ammonia at low temperature. This will reduce alkyne to trans alkene. Now that we have the alkene, we'll replace the allylic hydrogen with bromine. So allylic bromination from C to B, allylic bromination reaction. We need a source of bromine atoms, free radicals, so we use N-bromosuccinimide. We'll shine UV lamp onto the reaction flask and we'll carry it out in carbon tetrachloride with heat. This will give us secondary allylic bromide B. What's left to do is to eliminate HBr using base, KOH in aqueous solvent. Hydroxide will eliminate HBr to give us conjugated diene A. So the names of the chemical reactions going forward are alkylation of the acetylene or carbon-carbon chain extension reaction, followed by another such reaction to give us disubstituted alkyne, followed by reduction of alkyne to alkene using metal dissolving conditions. So this is not catalytic hydrogenation, it's reduction under free radical conditions, followed by another free radical reaction, alkylation, allylic bromination. This will give us secondary alkyl bromide B, followed by elimination of HBr, elimination reaction to give us conjugated diene.